Alright, so this is the second half of section 7.8, Improper Integrals. So this is Improper Integrals with Infinite Discontinuities. It's similar to the first half of the section where the endpoints were discontinuous, or the endpoints went to infinity. This one's a little bit different in the sense that the endpoints don't go to infinity, but one of the endpoints makes the function undefined. So the first one says, if f is continuous on the interval from a to b and has an infinite discontinuity at b, in other words, making it undefined, then you can take the limit as c approaches b from the negative side. And I believe this here is supposed to be a c, not an a. So let me change that. So this down here is a. This should be a c. So the limit as c approaches b from the negative side, or from the left-hand side of f of x dx. For the second one, if f is continuous on the interval from a to b and has an infinite discontinuity at a, then the following is true. It's the limit as c approaches a from the positive side, or from the right-hand side of the integral of c to b f of x dx. And for the third one, if f is continuous on the interval from a to b except for some value at c in the function. So if you look at the function and some value in this interval from a to b is going to make that function discontinuous, then you're going to have to account for that. So you're going to break it up around whatever point that is that makes it discontinuous. So in the first two cases, if the limit exists, then the improper integral converges, meaning you're going to get an answer, like a numerical answer for your integral. If it is not true, if the limit does not exist, then the improper integral diverges, so you'll get infinity or negative infinity or something like that. And in the third case, if either one of these two, excuse me, if either one of these two integrals from a to c or from c to b, if either one of them is improper, then it diverges. So you will not have an answer for that. It'll be infinity. So we're going to look at some examples. We're going to look at examples 6, 7, 8, and 9, I believe. We're going to start on page 537 with example 6. So if you want to look at that one, that would be a good place to start. Alright, so this is the integral from 0 to 1 of 1 over the cubed root of x dx. So I notice that if I plug in 0 down here at the bottom, I have an infinite discontinuity at 0. So I'm just going to make my little self a little note that says that I have a discontinuity at x equals 0. So therefore, at one of my limits, I have an infinite discontinuity, because if I plug in 0, that's not okay. So what I'm going to do is I'm going to take the limit as a approaches 0 from the right-hand side, from a to 1 of 1 over the cubed root of x dx. And, excuse me, if you take the integral of 1 over the cubed root of x, which is also x to the negative 1/3 power, you bump up negative 1/3, you get 2/3, and divide it by 2/3. So this would be the limit as a approaches 0 from the right-hand side of x to the 2/3 divided by 2/3 from a to 1. So if I rewrite this a little bit, I get the limit as a approaches 0 from the right-hand side of 3/2 times x to the 2/3 from a to 1. If I plug in 1, I get 3/2 times 1, minus, if I plug in a, I get the limit as a approaches 0 from the right-hand side of 3/2 times a to the 2/3. And if you plug in 0 to that, 0 to the power of 2/3 is 0, so 3/2 times 0 is 0, so this is just 3/2. So obviously the limit exists, so this series, or I'm sorry, this integral converges to 3/2, the area under that curve. Alright, let's look at example number 7. Alright, for this one we have the integral from 0 to 2 of dx over x cubed. Again, if you plug in 0, you have an infinite discontinuity at 0. So I'm going to say that I have a discontinuity at x equals 0, because it makes this function undefined. So I'm going to say that this is the limit as a approaches 0 from the positive side of the integral of a to 2 of 1 over x cubed dx. So if I take the integral of x cubed, I get the limit as a approaches 0 from the positive side of x cubed, that's x to the negative 3, bump it up 1 power, you get x to the negative 2 divided by negative 2 from a to 2. If I plug in 2 to this, I get negative 1 over that 2 times x to the second power. So if I plug in 2 to x, I get 2 to the second power, which is 4, minus the limit as a approaches 0 from the positive side, from the right side, of negative 1 over 2x squared. Or 2a squared, I'm sorry. So, for the first term, I get negative 1/8. For the second term, if I plug in 0 to the second term, as a is approaching 0, if I plug in that here, what's going to happen is I get negative 1 over 0, or negative 1 over a really small number, I should say. And when you have a number over a really small number, that number is actually blowing up huge. So this is actually infinity. Well, negative infinity because of the negative one on top. So then this negative here, and this one here is going to make a positive. So this is actually going to positive infinity. So negative 1/8 plus infinity is infinity. So this series is going to diverge. This is divergent. Unlike the last one, which is convergent. Because the limit goes to infinity. So therefore, you cannot calculate how much area is underneath this curve from 0 to 2. Alright, so the first one was an improper integral that converged. This last one was an improper integral that diverges. And now we're going to look at an improper integral that has an interior discontinuity, like the third case that we looked at. Alright, so like we said, sometimes there's going to be a discontinuity inside of the interval, so negative 1 won't give it a problem, and 2 wouldn't give it a problem, but 0 would give this one a problem. So you always have to check the endpoints, and then you also have to check if there's any points where that function, 1 over x cubed, where that function is undefined. So that function is undefined at 0, which is in our interval from negative 1 to 2. So we actually have to break up this interval around 0. So I'm going to break it up from negative 1 to 0 of 1 over x cubed dx. And I'm also going to break it up from 0 to 2 of 1 over x cubed dx. So for the first one, the upper bound is what gives us a problem, and for the second one, the lower bound is what gives us a problem. So what we're actually going to do is we're going to look at this piece, and actually let's just take a shortcut here. You could evaluate both of these things, so you could evaluate these integrals separately, which would be just fine, but I want you to notice that this is actually the one that we just did. If you look back at that last example, we did this exact same example, and I want you to notice that this one actually goes to infinity. So if you look back at rule number 3, it says in the third case, if the improper integral on the left, which is this piece here, if this improper integral diverges, so if either one of those goes to infinity, then this is going to diverge as well. So we automatically know that this diverges, that the limit does not exist, so we don't even need to really complete it, knowing that this piece alone is going to diverge. If you didn't know that, you could go through the process and notice that it does diverge. Actually, they both do. They both will diverge. If you didn't know that, then it would just take some extra steps. One thing I do want you to be careful of, however, if I can backtrack a couple of steps here, I do want you to be careful that you don't just automatically assume. So remember how in the beginning of this problem I said that you need to check the endpoints and you need to check the middle to see if there's any undefined points? If you had forgotten to check the middle and you just saw that the endpoints worked just fine, you might take the integral and get that it was x to the negative 2 over negative 2, and you might just take that integral from negative 1 to 2. And if you did that, you would get 1 over negative 2 times 2 squared, which is 4, minus 1 over negative 2 times negative 1 squared, which is 1, and you would get negative 1/8 plus 1/2, sorry, that's an eighth, plus 1/2, which would end up giving you 3/8. And obviously that's not the answer. So you just have to be careful to check that that 0 in the middle, that infinite discontinuity in the middle, would also give it an issue, because this is definitely not the answer. But if you forgot to check that middle point, then you would have gotten that if you had just gone straight for the limit. Sorry, straight for the integral. Alright, if you flip over to 538, we're going to look at number 9, example number 9 on that page, and that's the last one we're going to look at for tonight. Alright, so this is the last one. It's actually doubly improper. It's first improper because of that, so one of the limits goes to, one of the bounds goes to infinity, and then it's also improper because of this 0, because that 0 also makes it undefined in the function. So we have a doubly improper limit, and we can't evaluate the integral when both of the limits are improper. We can only do it when one of the limits are improper. So we're actually going to have to split this into 2 separate intervals, and you can kind of split it around whatever number you'd like. Normally we like to split it around 0, but because 0 is one of the endpoints, we can't choose that. So we would choose another easy number, which in this case is actually going to be 1. So if I split it up around 1, I get the integral from 0 to 1 of 1 over the square root of x times x plus 1 dx, plus the integral from 1 to infinity of 1 over the square root of x times x plus 1 dx. So, much easier now. These are both improper integrals, but I can evaluate them separately now, which is going to be easier. If you may or may not recognize which integral this is, but it's actually the arctangent one. So if you look closely, u is equal to the square root of x. Square root of x. A is equal to 1. So when you take the integral of the first one, you actually get 2 arctangent or tan inverse of the square root of x. And this first one is the limit as a approaches 0 from the right-hand side. So that's from a to 1. And the second one is also the arctangent, so 2 tangent inverse of the square root of x. Oh my gosh, I keep forgetting these limits. My bad. The limit as b approaches infinity of 2 tangent inverse of the square root of x from 1 to b. So, for this first one, when I plug in 1, I'll do it in red so you guys can see one at a time. When I plug in 1 here, I get 2 times tangent inverse of 1. And if you remember from our lesson last time, tangent inverse of 1 is actually pi over 4. So I'm going to write 2 times pi over 4. Minus, when I plug in a, and then if I'm taking the limit as a goes to 0, that would be tangent inverse of 0, which we talked last time was actually 0. So that would be minus 0. So that's that first interval. For the second one, if I plug in b, so here's what I'm doing now. If I plug in b right here, I'm doing 2 tangent inverse of the square root of b, which is the square root of infinity. And if you remember, tangent inverse of the square root of infinity is still infinity. So tangent inverse of infinity is actually equal to pi over 2. So this is 2 times pi over 2 minus, if I plug in 1, I get 2 tangent inverse of the square root of 1, which is 2 tangent inverse of 1, which we just talked about was pi over 4. So, this piece is actually going to cancel out with this piece. The 0 doesn't really matter. So all we're left with is 2 times pi over 2, which is pi. I don't even need that plus there. And that's the answer. So, short lesson today, that's all we're going to do. Just those 4 examples. I'll send the homework out in the school loop message.